fortunate to have Professor Jim Goodwin as our keynote lecturer. And Jim got his PhD at University of Michigan. He was a professor at University of Pittsburgh for many years, and then moved to Clemson. And if you're familiar with the Fischer-Tropsch literature, you know that he probably has more papers in this area of cobalt catalysis and catalyst design, kinetics, you name it. If there was anyone who is qualified to speak on the design of catalysts for Fischer-Tropsch, it's Jim Goodwin. We're delighted to have him here today, and he's going to talk to us about catalyst design. Jim.
Hope everyone can hear us. Thank you, Cal, for the overwhelming introduction. I think there are a few others in the room also who certainly know the Fischer-Tropsch area very well. It's a real privilege to talk to you today about some of the work that we've done and also some work that other people have done over the years. Particularly trying to give you an overall view of the design of the current generation of commercial catalysts especially. And of course, in the design of any catalyst, this is where you start. It's the playing field. For Fischer-Tropsch synthesis and CO hydrogenation in general, the group 8 metals are the metals that are active for this reaction by and large. So there are, of course, other things like carbides and things that can do some. And of course, if you get into methanol synthesis, if you want to consider that part of Fischer-Tropsch, copper zinc oxide is a commercial catalyst for that. But basically, when we talk about Fischer-Tropsch synthesis, usually we're talking about group 8 metals. And this is from a real classic paper by Al van Nuys, 1977. And sometimes the most classic papers are in some ways with the simplest idea. And this is a standard volcano plot, plotting turnover frequency for methanation of all the group 8 metals versus CO heat of absorption. And of course, what you see here is that cobalt is the most active metal for CO hydrogenation. And it, along with ruthenium, is much more active than almost anything else. It's a factor of many times and almost an order of magnitude more active than iron, and certainly more active than noble metals that you see way down here. Now, of these active Fischer-Tropsch metals, as you saw, cobalt is the most active, and of course it is the catalyst of choice for natural gas conversion, partly because it's got low water gas shift activity in general, and you can get some. And that's very useful because when you're converting gas, hydrogen is cheap and carbon is inexpensive. Ruthenium is a very good Fischer-Tropsch metal also, but of course you wouldn't want to load a whole reactor with pure ruthenium. It would be a little on the expensive side. Nickel is an active metal, good for methanation because you've got to run it at high temperatures because of nickel carbonyl formation. Iron is, of course, the catalyst of choice when you start talking about coal conversion or biomass conversion where you're dealing with low hydrogen to CO ratios. Because it's got good water gas shift activity. And it produces a wide range of products. Many of you in the room have worked with iron over the years, Bert Davis, Hans Schultz, and others around the room have seen this. Obviously, if you want to try to understand activity and selectivity, you need to understand a little bit the mechanism, and this is the mechanism of Fischer-Tropsch on cobalt, which is pretty well assumed by everybody now. There's been arguments over the years about whether the oxygen stays with the carbon longer or whether this decomposes into carbon and oxygen and get hydrogenates from there. But of course, for iron, CO dissociation is the flow step, and it's a big issue, and it's why when you promote with potassium, you boost the activity significantly. But for cobalt catalysts, hydrogenation is the most important step, or the slowest step, and so anything that impacts that tends to slow the rate down. And of course, you're dealing with the catalyst at the peak of the volcano plot, so almost anything you do to it makes it less active. If you try with promoters and things like that. And of course, you get chain growth and all these things that most people know. Cobalt follows Anderson-Schultz-Fleury distribution, like most of the Fischer-Tropsch metals do. And of course, alpha is a very key parameter when we're talking about the properties of a catalyst in terms of running it in Fischer-Tropsch synthesis. Now, if you want to try to understand the literature, you can either read, I don't know, maybe 1,000 patents or something like that. Certainly there must be at least 400 on cobalt, if not more than that. And if you take the whole bunch of them and you sort of group them by the companies that pushed a lot of the work, because certainly companies like Exxon have, well, there was 250 at last count, and maybe it's 300, I don't know by now, they probably continue to patent some. But starting with, and really what I'm talking about is the formulation of cobalt catalysts from the 1970s on, which is the latest incarnation of cobalt catalysts, because they date back to the 1930s and of course a lot of the German effort, and even right after the war effort in the United States and elsewhere to try to replicate a lot of the German work. Some of the earliest patents relating to commercial catalysts dealing with cobalt Fischer-Tropsch is really the patents coming out of Gulf. Ted Kobolinsky, Chuck Kibbe, and Rich Panel did a number of patents, excellent, that came out there. And basically those catalysts were on this top line. And I will go through a little more and define how I'm breaking them up. The other catalyst I'll talk about is Energy International, which was owned by Williams. The ExxonMobil patents now, obviously, Shell, who have worked significantly, Statoil, and Sasol. And the two efforts that I've been most involved in is Statoil and Energy International. And basically, to understand these catalysts, well, of course, they all contain cobalt. That's the first thing that makes them similar. They all contain, or many of them contain, a noble metal promoter. Some don't, for various reasons. They almost all contain, although not all, some sort of oxide promoter, both for activity reasons and for selectivity reasons, different promoters for different things. And of course, the most famous one is probably from the Shell stable of patents or whatever, the zirconium oxide that goes along with its support. And they all have supports, primarily alumina and silica, but there's titanium mixed in there as well. Now, there are a lot of other patents besides the ones that I'm listing here, but this captures where most of the commercial development has gone and what seems to work a lot. And of course, you know, this is geared towards making transportation fuels, diesel fuel. So, I mean, There are, of course, like the IFP patent, cobalt, copper, zinc oxide. We try to make high alcohols and other things like that that go off in other directions. Well, the support's the first thing when you're building a catalyst, and this is just to show you the three supports that you talk about. And of course, titania is a little bit of problematic because it's got much lower surface areas than the other two. However, some people have prepared very good, very active catalysts with this. It's more tricky probably than preparing catalysts on silicon aluminum to get good activity out of it. Okay, here's the promoters. Cobalt. That's what I call the noble metal +1 promoters because it includes rhenium. And actually need to take out one of those because no one in their right mind is going to put osmium in a commercial catalyst because of its toxicity. A lot of catalysts contain a selectivity promoter from the alkali series, and in more particular potassium because of cost and effect is sort of balanced there. And that tends to promote chain growth on cobalt catalysts, but at a penalty of rate. Then the last thing are oxide promoters, and what I'm highlighting is the ones that pop up often. It's the lanthanide series and zirconia, especially in the case of silica, and I'll tell you some of the reasons why. Now, other people have added other things, manganese, chromium, etc. All of those groups doing catalysis research to develop patents and all certainly have studied thousands of formulations. I've probably seen 1,000 formulations based on the periodic table. And of course, some things are better and some things give you high rates, but it's methanation and, so. But these are the ones that sort of settle down into the patents that tend to be the ones that look much more commercial in terms of applicability. Well, let's take a look at some support effects. And this is comparing the different supports, 1 atmosphere pressure in a fixed bed reactor. And you see, this is just unpromoted cobalt on alumina and silica, and you see their activities can be very similar under certain circumstances. And we always had trouble preparing a really active cobalt on titanium, but I trust in the abilities of Iglesia and Fiato and Steve Solad, so I know that you can do it because they say you can do it. But we were never able to reproduce their patents all that well. But Ed Blecken from the Norwegian Technical Institute told me yesterday that they've actually been able to reproduce some of that. Now, if you look at, obviously, fixed bed reactor at 1 atmosphere pressure is not where you're going to run a commercial process. So this is comparing a laboratory scale slurry bubble column reactor and these particular catalysts. And what you see is what you often see, and that is alumina tends to, when it's unpromoted, to be better than silica. And of course, as I said, we weren't able to get very high activity with titanium. Now you'll see these things come closer together when you start playing with the motors. Okay, let's take a look at the noble metal +1 promoters. And I won't go at all of them, and certainly some are more preferred than others. In general, rhenium and ruthenium tend to be the preferred noble metals for promoting it. People always worry about when you put platinum or palladium that you're going to get more methanation and things like that. If you keep it to very small quantities, you tend to be able to get good activity, and they do what they do, which many of you will know. And so this is going to be a series of catalysts, the cobalt ruthenium, pre-treated in different ways, and W stands for in the presence of water vapor, where we've added water vapor to really see the impact of that. And one thing that I have to tell you, there's another one of the classic papers that we cite all the time. We must have cited it probably in every paper we write on cobalt now, because Cal Bartholomew and his student did, developing a methodology for characterizing cobalt that works really well, where you have to do the adsorption at 100 degrees. Simple idea, but until you discover it, you can get really lousy data. Okay, so if you look at just cobalt on alumina, you'll see, well, it's pretty, 96 micromoles per gram of catalyst. That's not too bad. It's not that big a dispersion, but it's 28% cobalt, so 2.8%. Of course, if there's a presence of water, the amount of chemisorption goes down. But if you add the ruthenium promoter, of course, the chemisorption goes up. That means there's more exposed cobalt surface atoms, and the whole gain in cobalt rate is getting exposed cobalt metal atoms. And you can even see how this person, this is SEM pictures, because it's kind of hard to look with TEM at 28% cobalt on the catalyst. But you can even see the impact of ruthenium on helping to disperse the catalyst. You can see these large patches of cobalt. These are not single crystals, if you will, or large particles. These are actually colonies of particles. They cluster together. And I recently reviewed a paper who's done some film studies showing this happening for cobalt on an alumina surface. So it's very interesting to see in a very controlled environment. And you see in the presence of ruthenium, you're getting certainly what looks like better dispersion. In fact, that's what you see with the hydrogen chemical. Well, what is it doing? Well, there have been a number of papers, and certainly we've contributed to that as well. If you look at just the unpromoted cobalt, the cobalt on alumina, what you see is that if you do TPR of the as-calcined catalyst, you get some nice structures at lower temperature where you're getting reduction. But once this catalyst goes through reduction, it becomes harder to reduce, and you can see a drift upward in temperature of the reduction peaks. On the other hand, when you add, and by the way, this is more typical of the catalyst that you're using, because you don't do reduction in a TPR mode with 20 milligrams of catalyst or whatever. That's not a normal reduction for a commercial catalyst. Up here is the showing the reducibilities of cobalt ruthenium, and you see that yes, there's some change when you start pre-reducing the catalyst and recalcining it for running TPR, but you see maintenance of these low temperature structures. And what's important is really not what you can do with TPR all the way up to 900 degrees, because your standard pretreatment is a lot lower than that, typically for cobalt and alumina, 350 degrees. And that correlates with something like on TPR going up to about 400 degrees when you factor in kinetics and time and all these sorts of things. So you can see as the heat shifts to higher temperature, the catalyst is becoming harder and harder to reduce, and less is being reduced at especially in the presence of things like water vapor, and we'll talk more about that. So let's take a look at the effect of ruthenium promotion on reduction. These are the cobalt catalysts, the cobalt ruthenium catalyst. This is pre-treated with water. And here you see about, and this is pretty low, but again, this is not from the calcined catalyst, which is typically the way you would measure this. This is after reduction and consequently exposure to water. If you look at cobalt ruthenium, you see very high reducibility. It's very similar to what you would get with a calcined catalyst, 69%, 67, 53, whatever. And there's a lot of variables in here in terms of this percent reduction. So, if you want to look in the literature, you can find this varying quite a bit. There's probably a lot of variables in terms of how you handle the catalyst, how you ramp up the rate during reduction, because it all comes down to exposure. Okay, let's take a look at how ruthenium affects some of the properties, dispersion and rate. And what I call site activity, which is, those of you who know me know that we do a lot of isotopic tracing studies, and with a technique that we call Sitka, we can count the number of surface intermediates during reaction. And so this site activity is a reciprocal of the residence time, which is equivalent to the pseudo first order rate constant, and it's also equivalent to a turnover frequency based on the number of intermediates on the surface, reaction intermediates. Okay, the rate goes up, no surprising here, and of course I'm plotting a few data points, but it's based on a lot more studies than this, but that's not surprising. The dispersion goes up, or at least the chemisorption that you can measure goes up. That's not surprising. The number of surface intermediates goes up. Not surprising. You've got more surface area. But if you look at the turnover frequency based on the number of intermediates, it doesn't change at all, which says that the sites are not being affected by the ruthenium in terms of rate. And, you know, if you studied all of these, and we certainly haven't by all these methods, but what you'd find is that any of these noble metal plus one promotion increases catalyst activity, appears to accomplish this by increasing dispersion and reducibility, very key. Does not seem to affect site activity at all. And there's a number of papers that address this by at least more than a half a dozen groups, at least, I would say. And these noble metals basically facilitate the reduction of cobalt at lower temperature. But what about the oxide promoters? That was the one that had zirconia in there. Also in there is the lanthanide series, but especially lanthanum. Well, zirconium promotion, and this is cobalt on silica. What you see is that as you add zirconia to this, you increase the rate of reaction. Now, all these catalysts deactivate with time on stream, very typical plots for cobalt catalysts as it settles down steady state. But what you see is a huge enhancement, more than a factor of 2, by adding zirconia to these systems, and there's some effects of how you add the zirconia, what order, and what compounds you may use. So there's some subtle differences in there. But grosso modo, that's the effect. Add zirconium. Now, if you add too much of a good thing is bad. Once you start burying the cobalt, you're not going to have any activity of it. So with zirconia on cobalt on silica, there's a significant increase in the rate and no evidence of any significant impact on selectivity. Now again, we're not talking small effects or whatever, but in terms of things that we've been able to see. What if we look at, this is a comparison of cobalt on silica and cobalt, or zirconia promoting cobalt on silica, and you see in a fixed bed reactor getting about a factor of 2 increase. And this is comparing fixed bed and then a slurry bubble column operated at 32 bars, and now you can see, you know, this huge increase. And remember, this now puts cobalt zirconia on silica on the same par as cobalt on aluminum. And this is what makes cobalt silica work, really. It's a beautiful work that Shell did in coming up with this design. So significant increase in rate for zirconia promoted cobalt on silica. Now, what about on alumina? I mean, does it just have no effect at all? And the answer is, as you add some zirconia to this, you also get a boost in rate, and perhaps a slight impact on selectivity. But the biggest effect is an increase in rate. If you look at Dispersion rate, that's the dispersion. Basically adding the zirconia doesn't seem to affect the cobalt on alumina. But the rate goes up a bit, so it'd be sort of like saying, well, we must be promoting the catalyst, increasing the rate of something. And if you calculate a turnover frequency based on hydrogen, that's what it looks like. But if you look at it based on the number of intermediates on the surface, it's the old story. It's about getting more surface area or more exposed atoms, but really the rate on the sites are not changing. Okay, what about zirconia promoted cobalt on alumina, impact on hydrogen chemisorption and reducibility? Well, if you look at the chemisorption over here, there doesn't look to be a lot of difference. 118 versus 128, I wouldn't want to write home about that. That's not, you know, as Michel Boudard always said, unless it's more than a factor of 2, you don't get excited about it. This is about 10% difference. But if you look at the reducibility, the unpromoted catalyst has in TPR up to 400 degrees, only about 17% of the cobalt is reducing. But the zirconia helps in the reduction even on alumina catalyst, raising it to more than double the plain vanilla catalyst, if you will. Well, the other oxide that I mentioned is lanthanum, and you see this very often in patents. Of course, examples are usually given for lanthanum, and then everybody claims the whole lanthanide series, but that's the way you write patents, right? But in terms of lanthanum promotion, here is a cobalt on silica catalyst. And as you add lanthanum, you see a tremendous increase in the steady state rate. And in addition, in the case of the lanthanide series, you get improved chain growth. What about lanthanum promotion of cobalt on silica? This is the turnover frequency, because I'm not showing all the other data. But basically, you see, because we had Sitka data for this particular catalyst, you see that there's no change. The lanthanum is really not affecting the rate of reaction on the catalyst. It's having some impact on getting more surface sites exposed. Lanthanum promotion on cobalt on alumina. Dispersion actually that you measure with chemisorption goes down apparently. The rate goes to a maximum. Again, as you all know, too much of a good thing can be bad, and especially as you get to high and high loadings, depending on how the promoter associates with the metal. So if you start decorating the surface, you start blocking sites, or decorating the metal surface, I should say. But if and that's the turnover frequency based on hydrogen going to the maximum, not surprising because the dispersion didn't change significantly. But if you look at the turnover frequency based on the number of intermediates, there's essentially no change. You know, I mean, the small difference, about 15 to 20%, is within experimental error probably. But again, on cobalt on alumina, you also see improved chain growth possibility. So how do noble metals +1 and oxide promoters cause cobalt Fischer-Tropsch synthesis activity to increase? It's not by increasing the activity of the sites, but it's by increasing the cobalt reducibility and by increasing the cobalt dispersion. Why and how? And there have been a number of papers published in this area talking about it over the years, and this is very key, and it really comes down to, because all cobalt catalysts are supported on refractory oxides. And well known, going back into even before the 60s and 70s, a lot of work in Holland on nickel on silica and formation of nickel silicates and all. And so certainly this is a base metal, and of course it can react with refractory oxides. And the key element to making that happen is the water vapor. Because if you look at the thermodynamics of the reduction of cobalt, and if you said, okay, let's calculate this at various water to hydrogen ratios, which is what you're basically getting in a reduction scheme. Let's push it all the way up here to 10. Well, you're never going to operate a system with that high a ratio of water to hydrogen. You're going to be operating down here at worst. And of course, the bigger the quantity of catalyst you're reducing, the greater the concentration is going to be water exiting that reduction reactor or whatever, however you're doing it. But you're always going to be up here, and the catalyst will be 98% reduced. Because it's easy to reduce cobalt oxide and cobalt metal. So there's little thermodynamic limitation by water vapor because of cobalt. Now here is TPR after standard reduction of a cobalt ruthenium on alumina catalyst that has been exposed to various amounts of water vapor during the standard reduction. And this is how much reduction can be gotten as you go from 350, the reduction temperature, to higher temperature. And you can see as you add water to this, you greatly increase the amount of reducible cobalt that you couldn't reduce under your standard reduction condition. And in fact, this even shows it clearer, because here in the blue, as you add water, this is the amount of reducible under standard reduction conditions, reducible cobalt. This is what you can reduce up to 900 degrees, and this is the stuff that's not reducible at all. And this is some form of cobalt aluminate in the case of aluminum, and obviously silicated in the case of silicate. And you can even see the effects even in an SEM picture where highly dispersed metal clusters of particles or whatever, you don't see them as much. Certainly the big boys are still there because they are almost independent of the support. And so, what's the talk without a cartoon? There's the support. What's typically happening as you put cobalt on the surface and go through calcination, you make cobalt oxide rafts or clusters, some highly dispersed cobalt oxide, and that's probably the situation there. But during reduction, what can happen as you're forming particles of reduced metal, reduced cobalt, and probably there's some non-metallic cobalt that is interacting with the support underneath the particles. You've got some highly dispersed, hard to reduce cobalt, but what can also happen is you can get diffusion of the cobalt into the alumina, and it seems to happen during the reduction period. And there are all sorts of factors that affect it, because you might say, well, no matter what you do during the reduction stage, you're going to produce water in large quantities during the reaction stage. But it turns out that having carbon monoxide present helps in slowing the process down a bit. And so there is some protection of the different atmospheres that the catalysts get exposed to. Reduction at lower temperatures, of course, you create some more highly dispersed particles and all, and a lot less goes into the support at the lower temperatures, apparently. And with oxide promoters, of course, some of these can block the surface in whatever ways. Some things may bind with the alumina or silica or whatever, and some things may sit in between. But anyway, you can create a better dispersion with some cobalt, of course, going into the thing. So in summary, if you look at a whole host of site activities based on the number of intermediates for actually different conditions, for a wide variety of supports, for a wide variety of promoters, you see very little difference of, I think this is like half a dozen studies or more in terms of the change in that. And the differences that you do see are more affected by the partial pressure of hydrogen, because this turnover frequency based on the number of intermediates includes the impact of the surface coverage of hydrogen. So as you raise the partial pressure of hydrogen, you do bump that number up a little bit. And so that's why you're getting some of this range here. So basically, in terms of differences in site activity, there are none for a wide variety of supports, promoters. This is not everything, but pretty much not everything, not even close, but you get the idea at least, and you probably see this as pretty much what you see. And this actually goes back to a earlier work by the group at Exxon, Glacia, Soledad, and Giotto, who published the paper in 1992, and said that there were no effects of particle size and whatever. They were pointing to that it's all about reducible, in terms of rate, is what I'm talking about, but in terms of the amount of reducible cobalt, whatever. This was based on primarily reaction and kinabsorption data, I think, but certainly it anticipated all of the following results that came in more detail later. So cobalt catalytic properties are set by formulation, preparation, pretreatment, and reaction startup, and those of you who work with cobalt know what I mean. The catalyst is almost too active for its own good, and so it has to settle down a little bit, and if you creep up on it, it's pretty good. If you don't, you end up with a deactivated catalyst. The cobalt activity is primarily related to cobalt dispersion and reducibility. The key to getting high activity is to minimize cobalt support compound formation, either with noble metal promotion or with some sort of oxide promotion that helps block those entry points into the support. And especially useful to minimize the water concentration during reduction. And that's a key to everything. It probably has something to do with modifying the refractory oxides as well, and making it easier for the interaction. Finally, I'd like to acknowledge various types of funding over the years, both academic and consulting and all sorts of things. Interactions that I've had with various people are listed there who funded either me or my group or whatever. And I'd like to acknowledge all of the various research students, some in my own lab, some visitors like Sturla Veda from the Norwegian Institute, Technical University, and postdocs who worked on Cobalt Fischer-Tropsch, and various colleagues who worked with me on Cobalt Fischer-Tropsch over the years. Thank you for your attention. I'll be glad to answer any questions that I can.
We have time for a couple of questions.
When you spoke about the effect of water and the migration of cobalt into the aluminum support from cobalt aluminate, is it possible that the effect of zirconia promoters is that zirconia prevents that migration under the high water concentrations? So therefore, reducibility is higher.
Right, because when we do it on the same basis of without that oxide promoter, you get a lot more formation of the cobalt aluminate. So clearly it's a blocking action, or apparently a blocking action.
Back there. Please state your question as loud as you can.
Nice. There is one issue that you haven't. State very good, very good. There is no real effect on the intrinsic. That's what we see.
Say the last thing?
Well,
You said basically it was what?
there is no effect on promoters on the intrinsic turnover. But there is an effect on the turnover because there's a change in
On the hydrogen turnover, that's right, the dispersion.
Can you say something about how the promoters influence the site coverage that we see? See the difference, whether it's with
Right.
oxides?
Yeah, I mean, clearly there are a number of issues because you may be changing the heats of absorption or whatever, the hydrogen. So it could be that, like for instance, we've done some studies on cobalt on MCM41, and for some strange reason, we get what is known as hydrogen chemissorption suppression. It may not be true suppression, it just may be that at 100 degrees we can't populate the surface enough. We get good activity, so it blows the the hydrogen turnover frequency up. So yes, that's an issue. It's probably less of an issue for some of these systems than when you put a little more exotic promoters into the mix. But that's certainly a possibility.
I wish we could take more questions, but we have to move on. Let's give Jim a hand for